Welcome, everyone. This is Rana Nasser, structural engineer, PhD candidate, Cairo University. The following slides discuss our proposed methodology for seismic protection of wind turbine using vibrating barrier technique, VIBA. In this study, we explore the use of VIBA to reduce the dynamic response of the wind turbine under seismic loading. Under seismic loading. We all know that global warming is a dangerous threat for our planet nowadays. So there are many recommendations to turn to clean sources of energy to defend our planet, such like the recommendations of the Climate Summit 2022 to enforce the countries to turn into clean energy. The wind energy, which is one of the most powerful clean energy sources, become very reliable, and this become very reliable within these recommendations. So, so it become more used, and this make it immersed in high seismically active areas uh, to increase the wind energy sources. The problem here is that there is no sufficient literature studying the seismic analysis of the wind turbines. Many studies have been concerning on the protection of wind turbine against seismic loads nowadays, but most of them focusing on adding dampers to the turbine structure itself. So so the vibrating barriers, VIBA, which is an which is a passive protection technique, may be a very good solution for this situation. The VIBA technique showing very good results with monopile structures up to 44 reduction, as shown by Professor Kakula in the study in his study. It also it also tested with Dosser pyramid. It also tested with Dosser pyramid by engineer Maraz and Dr. Yusuf's team, and it gives about 30% reduction in terms of displacement response. And when it's used with artificial neural networks, the reduction reached up to increased up to 46%. So we decided to test this technique with the wind turbines in this study. Our objective, our main objective in this study is to enhance the seismic resilience of the turbines, either single or far, either single wind turbine or farm of wind turbines. We divided this goal to some minor goals can be measured. First, the dynamic response. The dynamic response simulation and data generation was our first objective, using finite element model to simulate the dynamic response of the turbine and generate data for neural network training. Then then design of seismic protection strategy using the vibrating barriers. After that, developing the neural network design tool, the neural network design tool to get the optimal design for the vibrating barrier we designed. The last stage, the last goal, the last goal is to evaluate the structural, is to evaluate the turbine structure before and after using the technique. Zafrana and Jabal الزيت wind farms will be our case study that we will apply our new technique. This is the location of Zafrana in Egypt, and here is the wind farms of Zafrana and the Jabal الزيت locations. Finite element, finite element model, finite element. A reference wind turbine, a reference wind turbine was used for the finite element simulation to validate which we can validate our model with. This is the simulated turbine and its characteristics. Here is the validation of our modeled turbine with the reference turbine, which show a very matching result. Then we started to validate that the Viva technique is an efficient technique with this type of structures, wind turbines. Several models were conducted with different Viva parameters, which provide that the technique show very good reduction in many cases, which was up to 50% reduction in acceleration response of the turbine. To find the optimum design, we decided to use artificial neural network. So we started to generate a large data set to be used in training this neural network. We used a Visual Basic application program to automate generating this data set, as shown in the following flowchart. The program generated about 10,050 and 500 models, extracted the results. Then these results were combined with earthquake data to form our dataset. The models that was generated was depending on the following criteria. The Visual Basic application was working on the models was created by changing the displacement from the displacement of Viva between the Viva and the turbine tower between 15, 25, and 35 meters. The mass also was varying between 300 kilonewton, half of the turbine mass, to 30,000 kilonewtons, which was about 5 times the turbine mass. The frequency also was changing in the range between 0.01 hertz to 24 hertz. The generated data was tested using shade analysis to check the quality of and sufficiency of the data in training the chosen neural network. That this analysis show very good uh, show very good acceptance, very good acceptance for the data, and the predictor of the importance showed that mass was the most important parameter of of the training dataset. Then we developed our okay the developed neural network. The developed neural network was a sequential feed-forward neural network. Was a sequential feed-forward neural network. This network was designed to process multi-source input data through a modular architecture, enabling modular architecture. The following schematic described the architecture of our neural network. The input the input layer was four branches. Uh, the, in, the, the network the network architecture starts with four input branches. Each branch initially processed by different number of hidden layers and different number of neurons for each layer, as shown uh, as shown in the schematic. Then, in this step, the network learns all about each input individually, then uh, then con then concatenate function was used to merge the four branches data together, and the network starts to learn about the relations between different inputs in this step. The next step, the next step, for the next step, the network starts to learn deeply about the combined data and create more relations between them. Then divide, and then divide this data to three branches, which are which connect between the independent, which connect between the input and the output um layers. Finally, each branch ends up to one neuron layer out. The number of layers, the number of layers and neurons in each layer, also activation functions, are all uh, resulted from a genetic algorithm which run a large scenarios of uh, neural network architecture and choose the optimum architecture of them. The network was training using the network was training using العقبة was trained using العقبة and دهشور 92 earthquakes, which are the most related earthquakes in our zone. Then, then the output, then the designs uh, generated from the trained neural network were tested using 5 different earthquakes, including Al-Aqaba and Dahshur, and other 3 new earthquakes. The earthquakes was chosen to be different in intensity, time length, and magnitude. Then they was scaled according to the guidelines of ASCII 7 to match the seismic zone of the turbine. After testing the vibrating barriers designed by the neural network, the highest response reduction was tested using 2 new different earthquakes that was not seen before for the neural network to verify its reduction capabilities. The VIBA design with the highest reduction was chosen as the optimum design of the VIBA for the case studies. There were different cases of dataset division to train the turbine was used. This training combination was tested to reach the perfect combination for the for the for the training, which gives the more accurate learning curve and the more efficient uh, reduction. The result in table 2, 3, and 4 shows reduction in the response about 47% in terms of acceleration at turbine hub point. Here is in table 2 the results of 40% of dataset training to testing ratio results for the first 5 earthquakes. As we can see, they're very efficient reduction we got from this combination. Then this is a 70-30 percentage reduction, which show also good reduction, but not good as 60%. Then here is the design testing, which shows here is the design the design testing, which shows the as we described, the design criteria proposed in this study was first train the neural network using 2 different earthquakes, Aqaba and Dashur. Then it will be the designs will be tested by 5 different earthquakes, uh, including Aqaba and Dashur earthquakes. The tested designs will be the tested design. From the tested designs, we will choose the highest reduction designs, the first 3 high reduction designs, which will be tested using another 2 earthquakes that the neural network have not seen before. This is the results of the the tested the tested earthquakes, the tested design with the different earthquakes, which shows uh, very high reduction, So we chose the most design which have very high reduction in all 5 earthquakes. The next step, we will complete the design testing criteria as described in the previous section using the optimum the design results from the previous step of testing to design Viva to resist the two new earthquakes. Then we will repeat the design testing criteria with multi-Viva single turbine conditions. The next step, we will repeat the design testing criteria with multi-Viva single turbine conditions in 3 dimensions. Then we will use the design testing criteria with multi-Viva, multi-turbine conditions on our case study, Zafarana and Jabal Zayt wind farms. The results will the results will be tested and structural evaluation of the turbine before and after the earthquake, before and after using Viva with the different earthquake will be generated. Thank you.